The Earth's interior notes that we did in class so that you can hear them again or you can hear them the first time. So the first thing that we did here when we did these notes was we took that inferred properties of the Earth's interior and moved some of the information here to this cross section, especially the density information. So here at the top we have the continental crust, and that's made up largely of granite and has a density of 2.7 grams per centimeter cubed. Right under that is the oceanic crust, and that has a density slightly higher of 3.0 grams per centimeter cubed. Under that then we're starting with the mantle. This whole piece here is the mantle. We'll talk about the parts of the mantle in just a bit. But we start at 3.4 grams per centimeter cubed, and as we go down through the mantle, it increases gradually until we get to 5.6. Then, this is the end of the mantle and the beginning of the outer core, and right here we have a huge change in density, 4.3 grams per centimeter cubed change in density. That is why there is a layer there. That is why we are no longer in the mantle. That is why we're now in the outer core. Just like our colored water made nice little colored layers because of a change in density, so does the Earth. Then once we're in the outer core, our density gradually increases again until we get 12.2. Then we have another jump, and we're in the inner core, and we go from 12.8 to 13. So big star over here, the layers change. We know we're in a different layer in the Earth when our density gives us a big jump. Pause this whenever you need. So let's go through the different parts of the Earth, the different specific layers. The lithosphere is this top layer here, and this is dividing up our crust into tectonic plates. And those tectonic plates are what we're going to do a lot with next. The asthenosphere here underneath is described as being plastic. Plastic, think Play-Doh. It is soft, it's a soft solid that holds its shape unless it is squished. So it changes shape with pressure. This is where the convection currents that move the tectonic plates are happening. As it gets hot down here, it gets less dense, and that soft rock material moves up, cools down, and back down again, moves down again. We'll talk more about convection currents on the back of the paper. The lower mantle is solid, but it is also that softish solid that allows the convection currents to move the heat and the rock from deep inside. We have upwellings where the rock softens, melts a little bit, becomes less dense, and then rises to the top. The outer core is a liquid. There is going to be a whole section in our study here of earth science where the answer is because the outer core is liquid. One fact to really stick in your mind there. But the fact that this is liquid iron and nickel is why we have the Earth's magnetic field. It is moving. We have the domains lined up for the iron, and we have a giant magnet, which gives us our magnetic field, which shields us from the sun's solar energy and from the solar wind. The inner core down here is a solid. It's the highest in temperature, pressure, and density. A little bit down here about how the Earth was birthed. We had meteorites orbiting the sun, left over from the sun, and they collide. That kinetic energy causes the Earth to completely melt, and those denser materials sink down to the center, the iron and nickel. But we can still look at the history of the Earth, the age of the Earth, the composition of the Earth when we look at the meteorites that are still falling. Those are just leftovers from the Earth as it was forming and tells us a lot about it. Flipping over to the back, we now have this diagram. Oops, okay, where am I at? The whole back, if we were going to give it a title, would be Convection Currents and the Effect of Heat on Density. This is the whole thing about density here. So looking down at our 3 heat sources. If I can get it to move down. Ancient heat sources are the kinetic energy from the meteorites hitting the Earth. The friction as gravity is pulling those denser materials down towards the core. But the only form of heat we have now is the radioactivity that's happening as large atoms decay. So, pull that back up a little bit, just a bit more. So this right here is radioactive decay. We start with plutonium in this example. 94 protons, 145 neutrons. Protons are positively charged. They do not like being together. They want to repel each other. Those 145 neutrons are doing their best, along with a strong nuclear force, to try and keep them together, but it doesn't always work. Eventually, they're going to decay. It's going to kick out an alpha particle, which is 2 protons and 2 neutrons. When this alpha particle leaves, a tremendous amount of energy is released. That is the energy that is keeping the Earth hot. So after we've lost 2 protons and 2 neutrons, we have a huge atom still. This is uranium, 92 protons, 143 neutrons. Those protons still do not like being together. It is still too big, and it will also decay and release more energy. We don't get down to stable atoms until we get down to about atomic number 82 or lower. So we've got 10 more protons here that don't like being there. And every time they release protons get shot out, then we have this energy being released. So that's our source of energy right now. So going back up to the top, maybe, where are we at? Spinning wheel of death. Oh, please no. Okay, so here we go. So let's talk about the 3 different methods of heat transfer first. Conduction, heat transfer by touching. So the inner core is touching the outer core, that's conduction. Frying an egg on a frying pan, the egg's touching the frying pan, that's conduction. Convection is where we're going to spend some time. This is the heat transfer with moving fluids. So as it heats up, it's actually carrying the heat, and it's carrying the material, it's carrying that rock up around with it. When you boil an egg, the water picks up the heat from the bottom and then brings it up and swirls it around, and that egg is cooked by convection when you boil it. Radiation then is heat transfer by waves, so we're microwaving it. Radiation is how we're losing the heat energy from the Earth. We are cooling down very slowly. The radioactivity can't keep up with us, can't keep up with radiation loss, but it's very, very slow. So let's talk about these convection currents down here. So it boils down to hot materials, and this is hot right here, become less dense. They want to move faster, they want to move farther, and they start to become less dense and they rise up. When they reach the top, though, they're losing heat by radiation, and so the part of the rock cools down. The particles start moving slower and closer together. They become more dense. Once they become more dense, then they sink down, pick up heat, and go around and around and around again. So cold materials, finishing this up down here, cold materials become more dense and sink. These convection currents happen in the Earth, they happen in the atmosphere, they happen in the ocean.
Jason Swartz, if you're in the building, could you report to the counseling office? Thank you.
Sorry about that. And they also happen in your pan of boiling water. Now we're going to keep coming back to these convection currents because they are what drives plate tectonics. So this little bit of crust here is a tectonic plate. And you can see that as this mantle material is moving here to the left, it's dragging this skin of a crust along with it. And that's when we're going to get earthquakes and volcanoes and all that kind of stuff. If you watched this all the way through, please text me peanut butter at 614-636-0331 and give me your name as well. Have a good night.